In section 8.4, we begin to analyze two-dimensional collisions. So our goals here are to apply conservation of momentum to both the x and the y dimensions separately in order to solve for final velocities in glancing collisions. So, do you remember what we said about collisions that took place in more than one dimension? Remember, momentum is conserved in each direction or dimension. So if we summed up all the momentum in the x direction, initially, that should be equal to all of the momentum in the x direction and the end of the problem or collision. Same thing would hold true for the y direction. So, for example, think about playing pool. That happens on a two-dimensional surface. There's lots of collisions that are going on there. Many of them are glancing collisions, where one ball hits maybe the second ball, and each of them end up moving off at some sort of angle from the horizontal. So if we were to look at an example like this, let's say that we have an object here that's going to be M1, it's going to be colliding with M2. Now we'll look at these angles here. We'll call this angle theta, and we'll call the other angle a phi. So as we look at these two angles here, we recognize that we could solve for the sum of the momentum in the x direction. Now, as we look at the initial problem has M1 kind of slamming into M2, while M2 was just sitting there at rest. So the initial momentum in the x direction is really just M1 V1. And in that case, we see that it's all in the x direction initially, and it's all from M1 because M2 was initially at rest. Now, as we look at the final part of the problem, where each of these objects end up glancing off at some sort of an angle, object 1, or M1, ends up having an x component to its velocity based off of the cosine of theta. So the final momentum in the x direction for object 1 would now be an M1 V1 cosine theta, whereas for object 2 up here, it also has an x component to its velocity, and that x component would again be related to the cosine of this other angle up here, which is an angle phi. So the final momentum for object 2 in the x direction is an M2 V2 cosine of phi. Now as we look at the y direction wouldn't have any momentum in the beginning because, again, remember our object was moving all in the x direction to start out with. So nothing is moving in a y direction to begin. There's no momentum in the y direction. As we look at the final conditions of this problem, we would see that M1 over here does in fact have a y component to its velocity that would be related to the sine of the angle theta. So the final momentum for object 1 in the y direction would be M1 V1 sine of theta. And for object 2, it would be going in the opposite direction. Here we called this the positive direction, that the negative direction. Remember, you always get to choose what you would like to call positive or negative, so that's up to you. So here we have the final y velocity of object 2, again having a component in the y direction based off of the angle psi and the sine of that angle. So the final momentum for object 2 would be an M2 V2 sine of phi, and again it's going in the opposite direction, so we could call that a negative direction. Or reverse the directions either way. Again, as long as you stick with your directions in your problem that you're solving, you'll be fine and get correct answers. Now, if this collision was an elastic collision, we could even write a third equation, which would mean that we could actually have a third unknown in our problems. Maybe an angle that gets thrown in there as an unknown along with the two final velocities that we're probably looking for. So with an elastic collision, we could write a third equation conserving kinetic energy. But if this was an inelastic collision, we would just have these two equations, which is basically conserving momentum in both the x and the y direction separately.